Now we're going to talk about coordinates and distance. And we'll start this discussion with what's known as the Ruler Postulate. The Ruler Postulate states that there is a one-to-one correspondence between the points of a line and the real numbers. It also says that the distance between any 2 points is the difference between the numbers assigned to them. So let's suppose I have 2 points, A and B, and their coordinates are these little a and little b. So this is our notation. The capital letter is the point, the lowercase letter is the coordinate of that point. Then the distance between a and b is the absolute value of a minus b. So this is the essence of the Ruler Postulate. And while this is true in Euclidean geometry, it's not true in spherical geometry. So we want to try to expand this idea to encompass both Euclidean and spherical geometry. So let's see how we can modify it. When we modify this, it's going to be axiom 6. So the Ruler Postulate says there's a one-to-one correspondence between the real numbers and a line. Axiom 6 is actually going to deal with arrays. So the first part of this axiom, there's going to be a one-to-one correspondence between the points on array, H, and the set of non-negative real numbers x, where x is between 0 and alpha, called the coordinates. So instead of assigning real numbers to every point on the line, we're going to do it on array. For Euclidean geometry, our endpoint will be 0 and will go up to infinity. For spherical geometry, will be between 0 and alpha. And these coordinates need to satisfy 2 conditions. The first, as I stated before, the coordinates of the endpoint of the ray is always going to be 0. All of the other points will have positive coordinates. The second thing it must satisfy, if I have point A with coordinate little a, point B with coordinate little b, and these are any 2 points on my ray H, then the distance between A and B is given by the absolute value of A minus B. So essentially, it takes our Ruler Postulate and just extends it to rays. So instead of entire lines, we're only considering rays. Our first theorem concerning this, if I have any 3 points on array A, B, and C with their coordinates little a, little b, little c, then the betweenness relation ABC holds if and only if either A is less than B is less than C, or C is less than B is less than A. So let's look at actually proving this. Let's start by going in the opposite direction. Let's assume A is less than B is less than C. From there, we can actually start computing their distances. Since we know A is less than B is less than C, we know we don't need the absolute values. We can say the distance between A and B is B minus A, B to C is C minus B, and A to C is C minus A. We then have that AB plus BC would be B minus A plus C minus B. We can simplify that to C minus A, which we know is the distance between A and C. So we have the relation ABC. And we can do something very similar in the case that C is less than B is less than A, and I'll let you go ahead and check that. For now, let's start to look at the other direction. Let's suppose we have the betweenness relation ABC. So now that we know that holds, let's consider all 6 permutations of our coordinates ABC under our inequality. So let's essentially just think of all of the different ways we can have these inequality relationships. So here are all 6 of our ways that we can have these inequality relationships. And I've grouped these purposely, so there's 3 groups of pairs. For this first group, we know we would need the betweenness relation ABC based on what we had done previously. If we know A is less than B is less than C, or C is less than B is less than A, then we know ABC holds. And we can do something similar with these other 2 groups. If we assume that either A is less than C is less than B, or B is less than C is less than A, we can use the previous ideas to show that A, C, B. And for our last 2 groups, we would get that BAC. So it has to be one of these first 2 cases. So we have our proof. The next thing we'll do is look at a lot of the properties of betweenness with these rays now that we have these ideas. Our first property, assuming we have three distinct points A, B, C, exactly one of these three betweenness relations must hold, either ABC, ACB, or BAC. The next one for betweenness properties of rays, this time I have four distinct points A, B, C, D. If I know I have the betweenness relation ABC and the betweenness relation ACD, then I'm able to say ABCD. Similarly, if I have the two betweenness relations BCD and ABD, then I'm also able to say ABCD. If I know I'm talking about rays and I have the betweenness ABC and BCD, I'm also able to say ABCD. If I know the relations ABC and ADC, then I can say either ABDC or ADBC. I can't tell you exactly which one, but we know it has to be one of those two. I also know that if I have the two betweenness relations ABC and ABD, then I can say either I have the relation ABCD or ABDC. And while I didn't actually prove any of these, I highly encourage you to try to use the definitions of betweenness to prove that one of these things, or that these things are all actually true. Let's look at a couple more properties. My next property, if I know the distance between A and B is less than alpha, then there exists a point E on my ray H such that A, B, E. So essentially, if I know the distance between A and B is alpha, then I can always find another point further along my ray than B. There's always at least one point after B. My next one, if the origin or the end point of my ray H is denoted by O, and I know the distance between OA is equal to the distance between OB, then we know that A is equal to B, provided both A and B are already on this ray. And once again, you can prove this one knowing that the endpoint, the origin, must be coordinate 0, and then you can prove it using the definition of distance. My next one, for any two distinct points A and B, there is a point C such that ACB. So if I have any two distinct points on an array, there's always a point in between them. I can always find a point between A and B. And once again, I encourage you to try to prove that these three properties are true. I'm not going to go in and verify them myself, but once again, like I said, I really encourage you to try to go in and prove each one of these.